The same thing, we'll see how it is going to work when we connect. Okay, so when we connect the real-time sensors with the hardware, and we're going to see the response also. So before that, if you have any queries, please let me know. I'm ready to clarify your doubts. If there is any queries, you can ask now. There is no doubt. I can continue. Okay. Okay. So if there is no doubt, let me continue. Yeah. Fine. So now I'll share my screen. Yes, I think you can see my screen now. Yeah. Okay. So we'll come back to LabVIEW. Okay. So morning we were discussing about the LabVIEW environment, how LabVIEW is used in different aspects. Okay, how LabVIEW is used in different industries and how it is used to develop different applications. So these are the things we were discussed in the morning session. And after that, so we have seen about LabVIEW environment. So how LabVIEW environment differs from other programming tool, and the most important thing is it is a graphical based programming tool. And we have seen about the different data types, and then about different functions. Okay, so which is used in LabVIEW for application development. Okay, so in that we have seen about case structure, we have seen about a while loop, and about the concept of shift register, right? And then now we are going to discuss. Okay, we are going to discuss about a for loop. After that, we'll be entering into the hardware concepts. Okay, fine. So hardware. Initially, I'm going to tell like how why what are the different types of hardwares are available. How we can simulate those kind of hardwares in LabVIEW. Okay, and after that, we'll see how we can develop the logics also. And finally, I'll be showing the real-time hardware. By connecting sensors, and then we are going to see the results also. Okay, so whatever the logic we develop during simulation, will it works fine exactly when we connect the real-time hardware here. Fine. So that's the agenda of the last session. So we have 2 hours, so last 10 to 15 minutes we'll have a hardware demonstration also. Fine. So let me start. Is there any query? No queries. Good. Okay, so the first thing we'll be discussing about for loop now, and now we have seen about what is the use of while loop. So while loop is used whenever you want to do any process in a repetitive manner. Fine. And the next thing is what? For loop. We can ask like what is the use of for loop. So whenever you want to do any process in a repetitive manner, okay. But if you know how much number of times you're going to do, we know that when we're going to use while loop, right? If you want to do any process for 10 times or 15 times, you need to develop or you need to write a logic write a condition to stop the loop here. But you know, we are going to run the application, or we are going to run a portion of application only for no number of terms. Okay, then you can finite number of terms, you can go for loop here. So here also, like structure text-based programming, we don't need to develop any logics here. Direct, no need to memorize any syntax. You can just take a for loop, drag and drop it in the block diagram. Okay, so this is how your for loop looks in LabVIEW. Fine. So as it is a graphical based programming language, okay, so we know that while loop has two terminals. Okay, one is your loop iteration, another one is your conditional terminal. In the same way, your for loop. Okay, your for loop also have two terminal. One is your I corresponds to what? So it's going to be a loop iteration, and then n. Okay, n corresponds to loop count. Okay, so this is a place where you are going to define how much number of times your loop is going to execute. Okay, here n defines how much number of times the loop is going to execute. So now I'm going to.
Sir, can you just show right from the new VI file how you came to this for loop?
Okay, ma'am, fine, yeah, no problem. So right now it is a new VI. Okay.
Yes.
So I have created a new VI. Now to use a for loop, right click on the block diagram, go to structure palette. In structure palette, you can see there is an option called for loop. Just click on the for loop, drag and drop it in the
The
block
block
diagram.
diagram, sir. Where is the
Ma'am,
block?
in block diagram, structure palette.
No, I am. I started this. Acha, in block diagram. Okay.
Which one?
Okay, sir. Okay, sir.
Okay,
Block
structure.
diagram. I am just writing it. Block
Oh,
diagram. I
and
have to
then
go
right click on
structure.
the block diagram and structure palette
Then.
in for loop.
Okay. Okay, sir. Thank you so much, sir.
Yeah, drag and drop it in the block diagram here. So you'll have two terminals. One is I is nothing but your iteration terminal, and N is going to be your loop count. So this is a place where we'll be defining how much number of times your loop has to get executed. So right click, create constant. Okay, so constants will always appear in the block diagram. Remember, only when you make anything as control and indicator, then only that will be displayed in your front panel. So if I define n value, okay, n value as 5, right? Then this for loop will run only for 5 times. Automatically, it will come out of execution. And here also, it will work. It will run at a very faster rate. So just see how much number of times your loop is executing here. It's a known number of iteration only. Let me give 500 millisecond, and to see whether it is executing for 5 times, create an indicator. Okay, and here also always keep it in mind, I value starts from 0. Okay, so let me switch to the front panel here, and let's and we can run the code. Okay, run. This for loop will run for 5 times. See 0, 1, 2, 3, 4. It will stop because always I starts from 0. So 0, 1, 2, 3, 4. So 4 times once the loop has completed its execution, okay, and automatically it will stop, it will come out of execution. So this is how a for loop works, and the main difference between while and for, you have to make a condition to stop your program. Here in for, you need to provide an n value so that your for loop will run for given number of times, and whatever the logics you write inside this for loop, that will run for that much number of times, and automatically it will come out of execution. Simple. We have done a sum of odd number, right? The same sum of odd number can be done in this for loop also. Okay, only thing is the loop changes. Apart from that, the logics is going to be same, but I'm not going to use the condition. So if I give 10 here, this for loop will run for 10 times. I can make use of this I value. Same, you have to find whether the number is odd or even. If it is odd, you need to add the number. And as I said, this for loop is running for given number of times, right? Here also, if you want to move, take your values, you present it previous iteration values to the next upcoming iterations, you can make use of shift register. So right click, and then you can see there's an option called add shift register. So automatically shift register will get added up. Okay, and then if you know that it looks black in color because we have not defined to which data type it has to store. When we pass any data type, and keep it in mind, shift register value is not used to store only the uh, numeric data. If you want to pass a boolean data, then shift register will memory will be assigned to store boolean data. Okay, so if I right click, if I add one more shift register, if I want, I'm just using a string constant. See, when I pass a string value to the shift register memory, it will store the string data information. So like this, you can create any number of shift registers in order to store the value. Only thing is, keep it in mind, shift registers are used to pass the value from one previous iteration. You can take the previous iteration value to the next upcoming iteration. Fine. So this is the concept of using your shift register, and these shift register option will be available only when we are going to work with for loop and while loop. Okay, fine, because these two are the structural functions which will be helpful to run your program or your logics for some known repeated number of times. Okay, so this is a small introduction about for loop and the explanation. Okay, and here also in while loop and for loop also, to pass the value we need to use channels here. Okay, so if you go more deeper and deeper, it takes more number of time, right? So here I'll just give a small outline. So whenever you try to pass any value, okay, whenever you try to pass any value, through your for loop or while loop, we'll be using tunnel. There are different types of tunneling modes available. Okay, there are different types of tunneling mode is also available here. Fine. So if you want to know what are the different types of tunneling modes available in for loop and while loop, right? So simple. If you want to see, if I try to pass the value, okay, if I try to pass the value through the for loop tunnel, and this is how the tunnel will appear. Okay, see, this is how the tunnel will appear. It looks new for you people. So the default tunneling mode for loop, okay, the default tunneling mode for loop is auto indexed tunnel. In simple form, we'll call it as indexing. So what exactly this tunnel defines is, when I right click create an indicator, always your output will be in terms of array. Okay, you will get an array of indicator. So now you are introducing to array also. Fine. So the default tunneling mode for loop is indexing. So this is how it looks. Okay, and if you want to check also, I place your cursor on the tunnel, right click and see there is an option called tunneling mode. By default, indexing is selected. Okay, indexing means it will get for this, the for loop runs for 5 times. For each and every iteration, it will collect all the values and then that will be displayed as an in an array of indicator. See, this for loop will run for 10 times and I value will be from 0 to 9. You can see all the values here. Okay, so if you want to check that also, see in front panel, I have an array of indicator, right? And you can see, sir, array you said it is a group of same data type. It has only one element, simple. Place your cursor on the border of array, drag, okay, you'll get the information once you drag it here and then you run. See, for each and every iteration, it will gather all the I values and then it will display the array of indicator. Okay, so this is what your indexing tunnel defines. Okay, when you work with while loop, the default tunneling mode for while loop is called last value mode. Okay, so what exactly your last value mode defines is, whenever your program starts, at the last time, whatever the value passing through the wire, that will be displayed in the indicator. Okay, even if you want to if you want me to show that also, I can use the last value here itself, but the default tunneling mode is what? Indexing. When I right click tunneling mode, there is an option called last value. Okay, when I right click create indicator, see, this will display the last value passing through the wire. If you see, we can see only the value 9. Okay, so there is a difference between last value mode. See, it is displaying only the last iteration value 9. Okay, but when you see indexing tunnel, it collects all the data and then displays in an array. Okay, so this is about the tunneling mode for your for loop and while loop. Okay, so with this, the basics about the lab environment is over. Actually, if you see, if you want to learn the complete lab environment, okay, if you want to learn complete lab environment about all the functions, okay, simple example in the block diagram, if you want to know about the structures, what are the structures available here, and about array and array functions, cluster and cluster functions, and about file IOs, okay, and we have something called architectures and all. To develop applications, we'll always use architectures. We have different types of variables, okay, so which is used to pass the data from one VI to another VI, like global variable, local variable, and even so. If you want to implement IoT based application also, it is possible using LabVIEW. You can access AWS cloud using IoT. You can access IBM Bluemix cloud. You can access ThinkWorks, and then you can work Google Firebase. So all those clouds can be accessed by using LabVIEW, but only few clouds are free where we can read and write the data, and few clouds are we have to pay and we have to get the access. So if you want to work with Google Firebase, it is free. You can read and write the data from to and from cloud, from LabVIEW to cloud and cloud to LabVIEW. IBM Bluemix, only we can push the data from LabVIEW to cloud. AWS also we can push the data from LabVIEW to cloud. But if you purchase, we can have two direction bi-directional transfer, okay, from LabVIEW to cloud and from cloud to LabVIEW. So that also we can do. And if you want to develop any machine learning based applications, right? So like supervised learning, unsupervised learning and all. So we have a machine learning toolkit here. So I think I have to check whether I have installed. I think I have not installed here. We have a machine learning toolkit. Once we install, we can work on KL, supervised and unsupervised learning. And if you want to work with deep learning applications also, so we can work on LabVIEW, like image processing based machine learning applications, or deep learning like object tracking, object identification, image segmentation. So those kind of things also can be done by using machine learning tool in LabVIEW, because mostly people will work on Python, but we work on actually LabVIEW. So we can do those kind of stuff. Okay, and if you want to do develop any applications and all, we'll be following some architecture. So to learn architecture and LabVIEW functions around, it takes around 5 days. But whichever is required for this FDP program, so the basic thing which you have to know to work on it. So those concepts only we are just speaking and we are just delivering from our side. So in future, if you wish to learn, you can just contact. So we'll give a support. That's not a problem. So we are ready to help and we are ready to provide a support for in academic people, especially because you as the faculties and then as people should know like how industry works, what are the different tools which industries are using, so that you can also work on that, and you are the people who are the backbone for the student, where you can just make your student to learn these industry tool apart from working on the normal Arduino or Raspberry Pi and all. Because if they work on these kind of industry hardwares in your academic itself, right, so they'll get an industry exposure, and they if they want to get a placement in core jobs and all, it will be very supportive. Most of the people who works on who is from the circuit branch and electrical, whatever it may be, right, finally they'll be pushed into the IT sectors. So there are n number of jobs are available in core side also. Only thing, it's an open statement. We couldn't find the right people to work on. Okay, because they are not aware of the tool. So because whenever we try to recruit any people, right, so only who is very good in the tool, and if they have knowledge on the tool, then only we can then pick, and then we can make them to put and work on the project. So if students are good enough on the industrial tool, and I'm not telling about lab, any other industry tool which they are using in industries to develop applications or testing, whatever it may be, right? If the students are good in that, so that they'll have an opportunity to work on the core sectors, fine. So because even it's from my experience, as I have done my post graduation also. So while doing my post graduation only, I just come to know that there is a tool called LabVIEW, and there are different automation tools available in the market, which is used in industry for automation and other application development. So then I just want to start my career in a course. So I have learned this tool, and then I just get into this domain actually. But now as the students, they have a lot of exposure. They can get everything in the internet. They can get the information through internet actually, and and the professors, you people also can share that there are different kinds of tools are available, which you can make them to work, or you can make them to do small mini projects or major projects, fine, major projects and all, so that when they go for core placement and all, that will be very beneficial for them, fine. So you can just take it as an startup, and if people are new, kindly work on this tool. Okay, fine. So with this, the concept of LabVIEW environment and the basics are over. As of now, this is these contents are enough to know about the basics. So there are still more things are there. So maybe in future, if we have an opportunity, if people can learn. Okay, fine. So we'll move on to the next part now. So it's going to be about similar hardware simulation. Okay, fine. So now I'll open a new VI, and we are entering into the hardware part. Okay, so we are entering into the hardware part now. Fine. So the first thing, why we'll go for hardware? Okay, so the first thing, why we'll go for hardware? Fine. So it's how we can have instrument control using LabVIEW, and we are going to learn about data acquisition also. Okay. So tomorrow you will be learning about multisim interactive analysis, and then you will be learning about multisim LabVIEW core simulation for system developments and all. Okay, and then using multisim also you're going to learn how you can go for instrument control and data acquisition using multisim. Fine. So today I'm just going to give an overview of the hardware. Okay, like how we can just simulate the hardware. Okay, so this one is for simulating the hardware and developing a code, and tomorrow you will be simulating the hardware, and then you're going to test the multi-sim circuits in LabVIEW. Fine. So those things you will be learning over there. So today I'm going to give the introduction about the hardware, and I'm going to just show a real-time demo also how I can interface the hardware and I can acquire the real-time data. Okay. So with this, let me get into the hardware topic. Okay. So the first thing, why we need to go for hardware. Okay. So whenever you want to measure, okay, whenever you want to measure any real-time physical phenomena, or if you want to measure any information through a sensor, okay, so then if you want to collect the data from the sensor, okay, if you want to collect the data from the sensor, and then if you want to analyze in a system using application software, obviously we need a hardware, okay, fine. So because hardware is going to act like a bridge or an interface which will help us to get the real-time data to our systems, okay, fine. So that is the main use of hardware. So today you're going to learn about a data acquisition system, okay, you're going to learn about the overview of the data acquisition system, fine. So what exactly means a data acquisition system, okay. So actually we call this as actually a PC based data acquisition system, because we are going to acquire the data in our system, okay, with the help of combination of hardware and the software, okay, and we're having the application software in a system, right, we are going to build the data acquisition system. So that's why we call this as actually a PC based data acquisition system, okay. Simple, this a data acquisition system will have a sensor, okay. We know sensors are used to convert your physical phenomena into electrical phenomena. Simple example, if you have a temperature sensor which is going to measure the ambient temperature, okay, and then it is going to convert that temperature into a voltage information, okay. In case if you want to measure those information, if you want to measure those information in a system, we cannot directly connect those sensors with your laptop or your desktop, okay. So we need some hardware interface, okay, we need some interface that's nothing but your hardware, where we'll be connecting the sensors to the hardware, and with the help of hardware only we are going to just collect the data to a system using an application software, okay. To build this data acquisition system, what other things are required? We need sensor, and then we need a data acquisition device, that is nothing but a hardware, and then we need the respective drivers, okay. We need respective drivers to be installed in your system, okay. So then only you can communicate with the hardware. Simple example, so whenever we people are connected from different place, okay, the common language which we can understood is English, so we are communicating, okay. The same way, if you want to just communicate with the hardware, we just need to know what language the hardware understand. Simple microprocessor, if you take microcontroller, you can just do a lot of applications and you can interact with the controller and the processor by using instruction set or assembly language programming. If you go and talk, the hardware doesn't understand. The hardware can understand all the informations through assembly language programming or instruction set. In the same way, you need to install the respective drivers in your system and the application software which is used to develop the logics. Okay, so the application software which we are using here is LabVIEW, and then we need to install the driver software and the DAC device along with the sensor. It forms a data acquisition system. Okay, so this is what a data acquisition system consists of. Clear? Okay, right. And the next thing, so what are the basic, okay, these are the 5 basic components of a data acquisition system. So once I explain about this data acquisition system, I'll tell you how to simulate the hardware also. I'll tell you how to simulate the hardware. And as I said, we have oscilloscope, we have function generator, okay. So without having a real-time oscilloscope and function generator, I'm going to generate a signal using virtual function generator, and by using the virtual oscilloscope I'm going to acquire the signal, okay. So all those things we are going to do now by using NI software and the NI hardware. To that together it's going to make a virtual instrumentation, okay, a virtual instrument, fine. So the basic building blocks of this data acquisition system, the first one is going to be sensor, okay. Transducers and sensors, we know that transducers or sensors are nothing but which will convert your electrical information into a physical information into electric information, okay. And next one is your signals, okay, the different type of signals which we are going to acquire from the sensor. If it is a digital sensor, it is going to give either true or false or high or low. Okay. If it is analog sensor, if it is a voltage sensor, it's going to give voltage. If you have current sensor, it's going to give the current value. And the third one, that is the most important thing, which is called signal conditioning. Okay, which is very, very important. Okay, signal conditioning. So, which is mainly used to condition the signal. We'll see in detail what exactly signal conditioning is. And the last one, Dac hardware, data acquisition hardware, and then we have drivers and application software. So a driver respective hardware driver, and the application software here we're using is LabVIEW. Okay, fine. So now next thing. So we are going to see like what exactly your see here. You can have this is the just data acquisition system of a DAC device. Fine. So here you can see we have sensor. So from sensor we are going to acquire the data. So we have the hardware here, which will have the signal conditioning options available, and we know all the things which are working is in terms of digital. We are in digital world now. We need to convert the analog signal into digital signal. We should use an analog to digital converter, and then leave about this embedded, because we are not going to see any embedded based hardware now. Okay, so directly through wired or wireless communication we are going to take the data to a system, which is, and then once you get the data, or once you collect the data from sensor through hardware to a system, you can have store the data, or you can analyze the data, or you can do data visualization, report generation. All those things can be done here. Okay, so this is the overview of data acquisition system. Fine. So simple sensors we know there are which is used to convert the physical information into electrical. And next, if you move on to signal, we have two signal. One is analog and another one is digital. Okay, so analog signals we can measure voltage, current, and then we can measure amplitude, frequency, time duration. All those things we can measure. When it is a digital signal, we can measure on state or offset of the signal, and then the rate of the signal. The most important third one is your signal conditioning. Okay, so why we need to go for signal conditioning? That is very, very important. As we know, the signals whatever we are reading, in order to convert that signal to be a readable signal. Okay, in order to make a signal to be a readable signal for a hardware, we need to go for signal conditioning. You can answer what exactly in signal conditioning does. Okay, so simple example, the most of the biomedical sensors, or if you go for any a thermocouple, a temperature sensor and all, okay, it's going to provide voltage in terms of millivolts. Okay, in order to be available as a readable signal, you need to amplify the signal. Okay, you need to amplify the signal. So for that we have to go for amplification. And the next thing, if you're going to work with any continuous signal, obviously noise will be present in that. In order to filter, in order to filter the noise information present in the signal, we'll go for filters. Okay, the third one, so to convert analog to digital, we'll use ADCs. Okay, so these are the three basic things of signal conditioning, where amplification, filtration, and then your conversion of analog to digital takes place. This is a basic thing which will be available in the data acquisition hardware, and these are what we call as signal conditioning modules. Okay, so before reading the information through the hardware, first the signals will be given to the signal conditioning modules, where the signals will get conditioned, and then through using your IO, input output cards, will be reading the information through the application software. Okay, and these are the different type of signal conditioning which we should perform whenever you are trying to read any information. Okay, fine. So this is about the signal conditioning. Okay, simple. See, if you want to work with, if you want to read any information from a thermocouple, you need to first do amplification and then linearization, and then you have to go for co-junction compensation. Okay, fine. And then if you see, if you go with any RTD, I need to go for current excitation, and we have to go for bridge wire configuration and linearization. So these are the few signal conditioning which will be taken care of by the signal conditioning module when we are going to work with those kind of signals. Okay, so this is a basic thing about the and then hardware. We know we are going to use data acquisition hardware, and then we'll be using application software. Okay, so today we are going to, there are different types of NI hardwares are available. Okay, so if you want to see that NI hardware, so if you see, and there are different families of hardware. Okay, instead of telling different types of hardware, there are different families of hardwares available in NI. Okay, if you see, we have two different families of hardware. One is called Dac family hardware, and another one is called Rio family hardware. Okay, and in detail, if you want to look on NI Dac family hardware, I can just directly Google it and I can show. Okay, so you can see here, these are the different types of NI DAC family hardwares which is used for data acquisition system. Okay, so today I'm going to show a hardware called, I'm going to show all the demonstrations finally by using a hardware called MyDAC. Okay, so there are, see, you can see here this one. Okay, this is what we call as actually CDAC, which is called as compact DAC, which is used for data acquisition system in industry, even where you can measure your three-phase voltage, you can measure high voltage and high currents using these modules. And if you want to measure any physical parameter like strain, pressure, flow, acceleration, vibration, whatever it may be, all those things can be measured by using this compact DAC, which is called, in short form we call it as actually CDAC actually. Fine. So this is one family or one type of DAC family hardware, and the most powerful hardware is what we call as actually PXIs. So this is what we call as actually PXI. Okay. So peripheral extension interface, which is mainly used for ATs, automated test equipment system. Okay, and an RF field and all the other higher end testing and AT development systems and all. We will be using this hardware called PXI hardwares. Okay, so this is also comes under a DAC family. So PXA has both a combination of Rio family and DAC family hardware. Okay, so this is how the PXA hardware looks. So there are different, and you don't think that to work with this hardware you need to learn different programming language. So whenever a DAC family hardware comes, okay, under DAC family we have MyDAC, we have CDAC, we have PXA DAC. Okay, PXA based data acquisition system, we have USB 6. See, this is also a DAC family hardware. Okay, so if you know to develop a logic for one DAC hardware, the same functionalities will be used in all the other DAC family hardware also. You can ask them what is the difference between why you have this much type of hardwares. Okay, so it depends on application. We need to choose the hardware. Okay, the hardware selection will be taken with respect to the requirement. Okay, so this is what we called as actually chassis. Okay, this is what we called as chassis, all the IO modules. Okay, see, so this is how it looks. Okay, it's a chassis. So this is what we called as IO modules. You can see here this image. Okay, this IO modules will be inserted on the slots of the chassis. Depends upon the requirement, you can select analog input card, analog output card, digital input module, digital output module. You can insert and then you can develop your application and you can make use of it for a data acquisition system. Okay, fine. So all these comes under what? A DAC family hardware. Okay, all these comes under a DAC family hardware. The only difference is what? Form factor. So some hardware may have Wi-Fi capability where we can transfer, read and write the data through Wi-Fi. Some hardwares will have USB based data communication. Some will have Ethernet based. So only that is the difference. Okay, and we have Rio family hardware. So under Rio also we have different types of families of hardwares are available. Okay, so we have this is called compact Rio, which in for short form we call as C-Rio, which is rugged in nature, which is mainly used for real-time application, and we can create standalone system also. Okay, and then we have another hardware called MyRio. Same, we have PXI based Rio. Okay, we have single board Rio. This is what we call as actually single board Rio. So where this is used for a different real-time application. I think we have seen a video called ball bearing sorting. In that, they have used this compact Rio and the vision inspection and the industrial controller, okay, motion controller to develop the logics here. Fine. So this is one type of hardware, and I think some people have asked about communication. So this is called NI USRPs. So this is mainly used for communication based research works and the project. So most of the 5G research, this NI USRP hardware is providing a huge support. And if you want to do any communication modulation techniques like a digital modulation as well as analog modulation, okay, ASK, PSK, AM, FM, and now the SDR, software defined radio, MIMO, massive MIMO, and OFDM. So all those type of communication research works, and in industries also the RF, okay, general I can say RF based communication. If you want to perform anything, you can make use of this USRP hardware. Okay, so and somebody has about WSN, wireless sensor network. Okay, So these are the NI hardwares, which is mainly used for wireless sensor network applications. Fine. So we have these much kinds of hardware. Okay. This is what I say PXIs. Okay. So PXI systems, which is mainly meant for AT purpose. Okay. This is how the PXIs will be. So we'll be having the IO cards. So we need to insert on the slots of the PXI, and we can develop the real-time systems. Okay. So these are the different families of hardware which we use in industries for real-time applications. And there are few hardwares which some colleges are using in their academics also, like MyDac, MyRio, all those things. So few of the some institutions, okay. So many institutions I think I have come across. So they're using NI hardwares for their research work and for the student application development projects and all they're using. Fine. So like this, you can develop you can use of these much types of hardware, okay, so to develop real-time application especially. Okay, so this is the introduction about the hardware part. Okay, next we'll be learning about how we are going to simulate the hardware. Okay, how we are going to simulate the hardware in your system itself. Okay, and then how we are going to develop the logics. Okay, how we are going to develop the logics to acquire and generate the data. And finally, when we get a real-time hardware, so we'll interface and we'll check whether the program whatever we develop supports when we connect a real-time hardware. Okay, fine. So think that you're going to develop some application. Right now you don't have the hardware. Okay, even though if you don't have hardware also, NI has the capability. It will help you to simulate those kind of hardware in your system itself. With that, you can just develop the logics. Once you have completed the logics, everything, right? Even you can check the output. Okay, logically you can just check the output. You will not get the real output here. You get some random value. If the system works properly, then you can connect your real-time hardware with your system, and then just change the IO configurations, and you can directly run your program to get the result. Okay, fine. So this is what we are going to do. So right now, I'm going to tell you how to simulate the hardware, and then let me connect and show how we can connect the real-time hardware with the system, and we can go for data acquisition. Okay, even I'm going to tell you how we can log the data in file. Okay, whatever the data you're getting from sensor, that data you can log it in your system. So that's what we call as data logging. But also, if time permits, I'll show a demonstration. Okay, fine. So with that, we'll enter into the hardware part. So today for the data acquisition system, so I'm going to show you about the DAC hardware. Okay, DAC hardware. So DAC family hardware under National Instrument. Okay. So in order to work with the DAC family hardware, you need to install the DAC driver. Okay. So that you'll get all the APIs or the functions which will help us to acquire and generate the data. Okay. And then if you install an software called NILBSMX, where you'll get all the instrument launcher. So for example, if you want to use oscilloscope, okay, NI virtual oscilloscope, when I select NI virtual oscilloscope, it will get loaded up. Okay, so instead of having, see, it's getting loaded now. Instead of having a real-time oscilloscope to measure and generate the waveform, okay, see, I can just make use of this virtual oscilloscope in my laptop itself. Okay, and then I can just make use of the NI hardwares, okay, to read and write the information. Fine. So this is how the virtual oscilloscope looks. You can see exactly how your oscilloscope, the function which a oscilloscope does. The same thing can be completely done by using this NI Elvis virtual oscilloscope. Okay, see, you have scales, you have time division, you have voltage division, and you can select the channels here. The oscilloscope has two channels. You can select it here. So all those things can be possible. Okay, and even if you want to generate the waveforms, if you want to generate the waveform also, you can go for function generator. So function generator. See, NILVSMX function generator. So for this and all, you need to install the drivers. See, I can generate sine wave, I can generate triangular wave, I can generate sawtooth wave, and the frequency up to 20 kilohertz. I can generate a signal, amplitude, offset. Okay, so all those things can be done by having this virtual function generator. Okay, at the same time, if you want to have a digital multimeter, okay, see, I have NI-LVS-MX virtual multimeter where I can measure voltage, current, and all those parameters by use instead of having a real-time multimeter, right? Uh, the which is available, which the existing multimeter, digital multimeter, I can make use of this. You can ask like how can we develop this? All these are like an EXE applications which is completely developed by using LabVIEW tool only. Okay, right? By using LabVIEW tool only, they have just created this UI. This is nothing but a user interface. For this, they have developed the logic. The block diagram cannot be seen because it is an EXE. Okay, fine. So these are the virtual instruments available in whenever you install the NILVSMX software where you can have those kind of virtual instruments. Okay, so next we are going to learn how we can access these virtual instrument, right? When we have the real-time hardware. Fine. So now first thing what we're going to learn now is how we can simulate the hardware. Okay, how we can simulate the hardware. So in order to simulate the hardware, so whenever you install LabVIEW software, along with this LabVIEW software, you'll get an option called, you'll get another option called NIMAX, which is called as Measurement and Automation Explorer. When you just click on this NIMAX, it will get loaded up, and then you will get this screen. Okay, I already have just opened the NIMAX. This is what we call as Measurement and Automation Explorer. This Measurement and Automation Explorer is mainly used to identify whether the hardware is connected in your system, and if your hardware has any configuration setting, then if you have an option for any configurations, right, you can make use of this NIMAX to do all the configuration. Even some of the even when you go for Rio hardware and all, you need to install the softwares inside the hardware. So for all those things, the NIMAX is required. And the most important thing is in order to simulate, okay, in order to simulate the hardware, okay, you need to install the respective drivers, then only you can simulate. So directly once you open NMAX now, after installing LabVIEW, if you try to simulate, it will not come. So you have to install the respective drivers. Okay, so as we are going to work today about the data acquisition system, okay, data acquisition system, so I'm going to show a demonstration. Okay, I'm going to show a demonstration how we can generate, okay, how we can generate, sorry, how we can simulate the data acquisition hardware. So the first step to simulate the data acquisition hardware is, see, there is an option called devices and interface, expand. Okay, there is an arrow mark over there, expand. So this will show how I can simulate the hardware. I just simulated different hardwares here. Okay, I just simulated different kinds of hardware. Okay, let it be. So now I'm going to show how we can simulate the data acquisition hardware. To simulate the data acquisition hardware, one second. So I have just simulated different hardwares here. Let me delete those, so or else you get confused. Okay, so to simulate the hardware, let me use the magnifier. Right click on the devices and interface. There is an option called create new. Okay, there is an option called create new. At the same time, here also you can see you are getting an option called create new. Both are same. Just give a click. Okay, once you give a click, it will direct you to another page. Okay, see, this is the next page which you will get. Choose the type of items which you want to add. Okay, so among this, there is an option called simulated NI DAC device or modular instrument. Okay, so select this simulated NI DAC device or modular instrument and then click finish. Okay, once you click and select finish, so you'll get an option to select which type of which hardware we need to simulate. Okay, yes, see, it is asking create simulated NI DAC device. We have different, as I shown, we have different families of Dac hardware. In this, I'm going to tell you how to simulate the MyDAC because I have the real-time MyDAC with me. I'll show you how the hardware looks and how we can acquire and generate the data. Okay, so expand, there is an option called educational hardware, and then you can see there's an option called NI MyDAC. Select this and then give OK. Okay, and automatically see MyDAC 2, a device is simulated You can ask how could you identify whether it is a simulated device. Whenever we simulate any data acquisition hardware, this USB symbol appears like golden color. Okay, fine. If it is a real-time hardware, it appears black in color. So this is your simulated hardware, and if you want to know, you can rename also. You can rename. See, my DAC sim. So this is just for our identification or reference. Which by reading this, you can easily identify it is a simulated hardware. Okay, the hardware name is now MyDAC2 sim. It is a simulated hardware. Fine. So your hardware is simulated. Now, okay, you can ask the question, okay, sir, we have simulated the hardware. And next part is how we can develop the logics. Okay, how we can develop the logics. Okay, and I'm just keep on telling a word call. I'm going to simulate a MyDAC. What exactly MyDAC is? How MyDAC appears? What are the I/O terminals available in MyDAC? Okay, all those things we need to know. Correct. That is the next step because we have just simulated a DAC, but we don't know exactly how your data acquisition hardware looks. That is very important. Okay. So, and what are the IOs available in your MyDAC? Okay, right? So, these are the things you need to understand. Okay, we need to know for that. Let me select this. I just connected a USB camera. So, I'm trying to just grab the image. I think have to look for USB Cam 3. Yeah, I think now it is visible. You can just look into the screen. So this is the hardware which let me just show properly. Okay, so this is the real-time data acquisition hardware. I just to show a demonstration for you people real-time demo. I just use some LED. Through this, I'm going to show you how I'm going to create a real-time traffic light logic controller using this data acquisition system. Okay, this finally I'll show a demo. So this is the NI hardware. Sorry, yeah, this one. Okay, so this is called MyDAC, which is mainly used for data acquisition purpose. Okay, so it comes under a family called Dac family hardware, which has analog inputs and digital output pins, where you can build a data acquisition system using this hardware. Okay, so today we are going to learn about this is the hardware which we have simulated. Okay, I have a real-time hardware with me at the same time. So I'm going to just a moment. Yeah, fine. So with this only, I'm going to show a data acquisition demo. Fine. So you can see this MyDAC has a DMM probe. See exactly what your multimeter have. The same DMM probe is the DMM option is available here. Through this only, if you have the DMM connectors, okay, the probes, you can just interface with the terminals, and you can open your digital multimeter, whatever we have here, right? This digital multimeter, and you can measure the voltage, current, and the other parameters by using this hardware. Okay, see this hardware and this virtual digital multimeter together forms a virtual instrument. Okay, fine. So when I have the probes, I can just insert it here, I can connect, and then I can measure, if I run this, and I can measure the voltage as well as current and other parameters. Okay, so and along with this we have some IO terminals where we can connect the sensors, and then you can read and write the data. Okay, so this is how we can simulate the hardware. Okay, we can simulate the NI hardware. So I have just shown a demo how to simulate the data acquisition hardware called MIDAC. Okay, I just shown you how to simulate the MIDAC. The same way you can simulate the other different types of hardwares also. Okay, the DAC family hardware. Rio, the steps are a little bit completely different, so that is not in our picture for the day. Okay, so this is how we have to simulate the hardware. Fine. So with this, the simulation. Okay, how the steps to simulate the hardware is over. Next step is what we are going to learn how to read and write the data. So before that, we'll see the specification of the simulated hardware. Okay, what exactly the hardware does, what are the number of IOs available in the hardware, what are the things which can be possibly done with the help of hardware. So one by one, we'll see. Okay. So let me know if you have any queries, any doubts. Okay, so if there is no doubt, we'll move into the spec or the data sheet. Yeah, so this is the spec of the DAC hardware which we have simulated right now. Okay, and see, this is how your DAC hardware looks, which I have shown through the USB cam. Okay, and it has a DMM probe, and this is a place where we have IO terminals. So let me just move on to the pinouts. See, this is how your MyDAC hardware looks, and as it is an electronic device, it needs a power. So, and this hardware is interfaced by using USB. So through USB only, it is going to read and write the data at the same time. It's going to provide power for the hardware. And this is a place where you can just use connect your DMM probe, see DMM cables to measure the voltage and current by using the multimeter. And here you can see I have the number 5 is to connect the audio. Okay, even if you want to acquire the audio, or if you want to generate an audio signal, real-time audio signal. Okay, for example, if I have an headphone, okay, if I talk, if I have a microphone, if I want to acquire the information to my lab view, and then if I want to do any process, you can just use a microphone and connect to the audio input terminal. Okay, and then you can acquire the information. And what is the use of audio out? Okay, audio out is mainly used to send the audio signal. For example, if you are generating an audio signal and if you want to send it, okay, send it out through the application, so you can make use of this audio terminal. When we connect the respective speaker or something, we can just hear the audio signal. Simple example, if I have a mobile phone, if I have the audio cable which will come along with the MyDAC, so I can just play a song in the mobile phone, I can acquire the song to my lab view, and then I can develop an audio equalizer, and then if I connect my headphone to the audio out terminal of the MyDAC, I can hear the song, okay, through my LabVIEW data acquisition system, not through my phone. So from my phone, DAC will acquire the signal, and in LabVIEW the signal will get processed, and then I can hear the signal, hear the song or the audio through my MyDAC hardware. Okay, so those kind of things can be done by using this hardware, and these are the pinouts. Number 4 is your pinouts, where we can connect the IOs, okay, the sensors through the to the MyDAC hardware. Fine. So this is the pinout configuration, which is very important. The hardware which we have simulated, okay, which we have simulated is MyDAC. It has audio input and audio output terminal, which is used for generation acquisition of audio signal. And if you look here, okay. So I have 5-volt and digital ground. If you have any circuit which needs a power for excitation, if it is a range of 5 volt, you can make use of it. I have digital ground, and you can see 0 to 7. So 0 to 7, I have digital input outputs where I can connect, okay, where I can connect this digital type of sensors. Okay, see, it is mentioned as DIO. It is not DI or DO. It is DIO. DIO means which is digital input and output. Okay, either you can configure those pins as digital in, or you can configure as digital out. Okay, for example, I have 0 to 7, totally 8 digital input output pins. So depends on the requirement, you can select few pins as digital input and you can select few pins as a digital output. Okay, fine. And the next one you can see I have AI in bracket, they have mentioned as plus or minus 10 volt. The most important thing which I'll always tell to everyone, so whenever you're trying to work with any sensor or any hardware, kindly go through the data sheet and the specification, because if you provide any info signal, okay, to the hardware without knowing the specification, if the signal range is beyond the limit, the hardware will get damaged. So kindly go through the data sheet, and especially this Dac hardware can measure only the voltage signal. Okay, that voltage signal. Okay, that voltage signal range will be in terms of plus or minus 10 only. So we have totally two analog input channel. So it's 0 plus 0 minus combinedly one channel, 1 plus 1 minus together and another channel. Okay, and then I have analog ground. A, G, and D corresponds to analog ground. And then I have two analog outputs, AO0 and AO1. And then I have analog ground there also. And then I have 15 volt plus and minus 15 volt, which can be used for excitation. Okay, so these are the pinouts which is available for your Dac hardware. Okay, and this real-time hardware is simulated with the help of N9 Max, which is called Measurement and Automation Explorer. Okay, and if you want to look into the specification, which is very important, so this one. Analog inputs, we have two different two channels, differential configuration, and the ADC, that is very important. Okay, ADC which they have used here is a 16-bit ADC. So whenever you have high resolution ADCs, okay, if you have high resolution ADCs, even a small change in your signal will be available as a readable signal. See, maximum sampling rate is 200 kilo samples per second. Okay, fine. And the range, see, plus or minus 10 volts, plus or minus 2, and DC couple. And for audio, okay, audio input, it is plus or minus 2 volts. Okay, so if you're going to acquire any audio signal, it should be in a range of plus or minus 2. Okay, and the connector, it's a screw terminal. Fine. And then you can see, so this is your analog output configuration, two channels, DAC, digital to analog conversion, 16-bit DAC, and then you have sampling rate is around here also 200 kilo sample. Kindly look here, the analog output here also, it can generate only analog signal. The range is plus or minus 10 volt. Okay, and plus or minus 2 and DC couple, right? And analog output plus or minus 2 volt. Fine. At the same time, we go for digital input output. See, it has 8 digital input output line. So each lines you can individually program. At the same time, it has a counter also. You can go for counter operation. We have one counter here, and if you want to generate a PWM signal, the PWM pulses, okay, that is also possible. In order to generate a PWM signal, especially for when they're working on the converters. Okay, so for electrical people, if they're working on converters, right, so they'll be generating the PWM pulses in order to provide in order to boost or reduce the output voltage of the system. Okay, and those, for if you want to control the motors, okay, if you are going to control the speed of a motor, to the motor drivers you need to provide the pulses in order to have a speed control of motor. So for all those things, to generate a PWM signal, Dac has a capability to generate PWM signal. It has one channel which will help us to generate the PWM signals. Okay, so these are the basic specifications which we need to know before simulating the hardware, because blindly we should not simulate a hardware. We should know what exactly the hardware does, what is the specification of the hardware, and what are the how many number of IOs are available, and what is the range. Okay, what is the measurable range of what are the signals which we can be measured using the hardware. So by knowing all those things only, we need to simulate the hardware. So we have simulated the Dac hardware, and this is the specification about this data acquisition hardware. Okay, the next part is what we are going to learn. Okay, how to develop. Okay, we are going to learn how to develop a logic to read and write the information, okay, either in terms of digital, at the same time in terms of analog also, okay, fine. So first we'll look into digital, how we can work on how we can read and write the information through a digital signal, and later part we will move on to analog also, okay, how we can develop a logic to read and write analog signal, and finally we'll implement those using your real-time hardware to check whether it is supporting, okay, the same configuration, whether it is supporting for the whether the logic is supported whenever we connect a real-time hardware, fine. So now the next part, I'm moving into the programming part. The introduction about the hardware, okay, is over, fine. Please let me know if you have any query. The specification and about the description about the hardware is over. Next part, we are going to learn how to develop the logics. So if you have any queries, please let me know. Any doubts? No doubts? It's clear? If you have any queries, please let me know. Yeah, thank you. So if there is no doubt, we'll proceed further. Okay, simple. You have to open a VI. Okay, so once you open a VI, and the important thing is there are two different ways to develop the application. One is using high-level VIs, and another one is using low-level VIs. Okay, so as when you're new to the hardware part, initially I'm going to show how we can write the logic using high-level VI, and next I'm going to show how we are going to write the logic using low-level VIs. Okay, one by one we are going to see. Fine. So the first thing is what? Right click on the block diagram. Okay, and if you want to work with any data acquisition hardware, make sure the driver should be installed, and those functions, okay, those functions will be available in measure. There is a palette called measurement IO. Inside this measurement IO, if you see, there is a palette called NI Dac MX. Okay, when I place my cursor over there, you can see the first one. I have a palette called NI Dac MX. So when this palette is available, okay, which means that you have installed the data acquisition hardware driver, which this functions can be used to do any data acquisition application in case of PXI, CDAC, okay, or MyDAC, or USB DAC, or Wi-Fi DAC, whatever it may be. When it comes under DAC family, the same functionalities are used to develop the logics here. Okay, so let me just look into this NI DAC MX. I'll pin it out. Okay, because these are the functions we'll be using to read and write the logic. So as I said, right now we'll come to know what is the use of the LabVIEW environment. Okay, so because these functions are only used to read and write the information from sensor. Apart from that, all the analysis purpose will be taken care in LabVIEW using all the LabVIEW basic function. Okay, so to read and write the information, we'll start off with a digital. We'll select data acquisition. Okay, DAC assistant. So in short form, we call it as DAC assistant. Just select and then put it in the front block diagram. Okay, so once you put that DAC assistant in the block diagram, immediately you'll get a pop-up. Okay, immediately you'll get a pop-up here. See, it is initializing now. Yeah. So once I just place this, you'll get a pop-up. See, you are getting two options. Okay, and now here two things. Okay, you can see one is called, excuse me. So one is called acquired signal and another one is called generate signal. Okay, so here two things. Acquire means you are going to read the information from sensor. I'm telling you clearly. Acquire signal means you are going to read some information from sensor through Dac hardware. Okay. Generate means you are going to send some signal from your LabVIEW tool through Dac hardware to the environment. Okay. Simple. Acquired signal means you are trying to read the information from sensor through Dac hardware to your LabVIEW software. Okay, clear? Generate signal means you are going to generate or you are going to send some signal from LabVIEW Dac to the outer environment. Okay, fine. This is the difference between acquire and generate. Please don't get confused. Okay, and now when I just expand acquire, when I just expand acquire, I have
Sorry, your voice is not audible.
Voice is not.
sorry, I think due to some network interruption, the connection has been lost. Okay, thank you. I think now it's audible. Thank you so much. Thanks for the reply, sir. So we'll go to the logics. Yeah. See, so these are the different options available to simulate the to select the IOs of the respective hardware. So right now we are going for simulation based. Okay, so because you people also don't have the hardware, you can just simulate. Just expand the simulated DAC options. You have line 0, line 1, line 2, line 3, line 4. So whichever the line you need to select, and then you can just provide finish. Okay, and after that you'll get one more pop-up. So you have just selected the line now. Okay, you have just selected a line, and we have configured what acquire, which means you're going to read the digital information here. Okay, and then you can see, and if I provide okay, and now this DAC assistant. Okay, now this DAC assistant is configured. Okay, this DAC assistant is configured to generate. Okay, which is configured to generate a digital, sorry, which is configured to acquire a digital signal. See, it is showing building a VI, right? Depends upon the user configuration. At the back end, a VI is developed, okay, and now this is ready to acquire the digital data. Okay, and now it is ready to acquire the digital data. And if you right click and create an indicator, you'll get an array of indicator, because always this output is going to be an array of indicator. If you run the program also, will not get the output, because we are simulating the hardware now. Okay, so this is up to the programming part only. So once you get the real-time hardware, you can just connect and then you can read the output. Okay, fine. So but the multi-sim data acquisition is completely different. Okay, this is only to learn how we can just simulate the hardware. We can develop the logics. Okay, later part to see the real-time outputs, we can connect the hardware and just only we can change the IO configuration. Immediately you can read the output here. Okay, so instead of waiting for the hardware, right, you can just develop or you can complete your applications. So this is how by using a DAC assistant you can acquire a signal. Now it is a digital signal. You can ask the question. It's only a simple block which is used for acquisition. But if you want to see, it has shown an option called building a VI. And if you see the front panel, okay, if you want to see what is the logic built behind to read the digital signal, so this is the logic which was completely internally developed by LabVIEW to build the to acquire the digital signal. Okay, you can see here the use of while loop, the use of shift registers, and the case structures here, and we have used for loop. Okay, and then here also case structure loop. So depends upon the requirement only. We'll be developing the logics. Okay, you can ask a question. This is the use of high level. Okay, but the same thing can be developed by using low level VI functions. Okay, so you can see I have different functions here, which is called create channel, read, write, wait. Okay, all these together only this block has been built. But as a new, whenever you're introduced to the data acquisition hardware newly, we'll always suggest you to work with the DAC assistant just to know what is happening, what are the steps you are following to generate and acquire a signal. Once you're familiar with the DAC assistant and the steps, and then we'll tell you how, we'll always tell how to make use of these functions, okay, in order to read and write the signal. At the final, I'll show a demonstration how I can use the low-level VI also, but always we'll prefer low-level VIs for application development because it will be more user-friendly, because few of the configuration settings and few informations cannot be given during your program execution during when we use high level VA. But when we have a low level VA, you can interact with the system. You can change the few configurations and the parameters which we are passing during your program execution state also. Fine. So this is how you can acquire the generate signal. Now what I'm going to do is I'm going to develop a real-time logic. Okay, I'm going to develop a real-time logic. I'm going to generate. Okay, I'm going to generate a digital signal. Okay, and then we'll see how I'm generating a digital signal using now real-time MyDAC hardware. I just shown how to simulate, or I have shown how to acquire signal using simulate DAC. Right now, I'm going to show how we can generate a digital signal, okay, and how it is going to pass out of the MyDAC hardware. Okay, so for this, if you look in the camera, it's USB 3, yeah, you can see in the camera I have 3 LEDs with me. Okay, you can see here I have 3 LEDs, red, green, and then yellow. Okay, so I'm going to just show, I'm going to control the on and off status of the LED. Okay, I'm going to show the on and the, I think it's visible now. Yeah, it's fine. Okay, I'm going to show how I'm going to control the on and off status of the LED. And if you want to look into the connections here, I need to show like this. You can see, right? So LED comes under digital because I'm going to on and off. So this connections, whatever I made, it is for to show you how a demonstration on a traffic light logic. Okay, so right now I'm going to show how we are going to control the on and off status of single LED, not multiple LED, single LED. First, we'll try to see how we can the on and off the red color LED using my Dac hardware. So here we know it comes under a Dac family. Okay, it comes under a Dac family, right? So if you look the connections, if you look the connection here, so we have, let me slightly more. Once again, yeah, I think now it is quite okay. See the connection which I'm going to do. So one I have connected to digital ground, which is common. So I just selected 3 digital lines. You can see DIO0, DIO1 and DIO2 for 3 LED. Now I'm going to choose only DIO0. Okay, I'm going to choose DIO0 and then I'm going to make this LED to get turned on and turned off. Okay, and this LED is connected to, okay, DIO0. Okay, fine. This connected to DIO0. So why I made this connection before, because if I start to do all the connections, right, it takes much time. So instead of that, I can show a demo directly. I can explain few more concepts. That's why I already during the lunch break I have made this connection. Okay, it's very simple only. So let me develop the logics to turn on and turn off the LED. Okay, I'll show for one LED. I'll show how we can just generate group of digital signals step by step. Okay, initially we'll see how we can generate a digital signal. Second step, we are going to see how we are going to generate multiple digital signal, and then we are going to see how we can control or how we can develop a traffic light logic. Okay, because we have red, yellow and green, right? I just interchanged, so that's not a problem. So I'll develop a logic first. So measurement diode, okay, measurement diode DAC MX, and then I have an option called DAC assistant. Let me select the DAC assistant and then place it here. Okay, once I place the DAC assistant, we know that we are going to get a pop-up. So now I'm going to turn on and turn off the LED from LabVIEW, which means I'm going to send some on and off signal from LabVIEW through DAC to the LED. Okay, so then I need to use what? Generate signal. So after that, we are going to generate digital or analog. It is a digital signal. Expand digital out and go for line output. Okay, go for line output. Now I'm using a real-time hardware. If you want to check which hardware is connected, see it's MyDAC1. Okay, I have a hardware called NI MyDAC1. The USB symbol appears black in color. See the status is present. This is the hardware which I am using to generate and acquire the signal. Okay, so select MyDAC1 and let me select line 0. Once I select line 0 and select finish, okay, and you can see, so it is going to send the digital signal. See, that's why it is digital out. Okay, it is digital out here. Okay, and if you just done this, okay, so it is going to send a digital signal out. Fine. So now you can just provide okay. It's building a VI. See, now it is asking an input. Now it is asking an input, right? So to control the LED, let me have a Boolean control. See, it is a push button. Okay, I don't have. I'm going to control a real-time LED. And now, if you see, when I connect this control to the data input, it is showing an error. Okay, I'm getting a broken wire. So there is a shortcut called Control B. Okay, we have a shortcut called Control B to remove the broken wire. So why I'm getting a broken wire? Okay, and if you want to know what is the reason, so what you can do is place a cursor here. See, it is telling you are connected two terminals of different data. The input is a scalar one and the sink is going to be a one-dimensional array. So it will accept always an array as an input. Okay, next step, we are going to learn a new function here which comes under array category. So whenever you want to convert a scalar data into array, okay, go to the array palette, there is a function called build array. Okay, there is a function called build array which will convert your scalar data into array data. So connect it and then connect here. Okay, now it is connected, and to run your program continuously, what we need to do, you have to use while loop. Okay, and we need to use a stop button. So right click on the conditional terminal, create control. Okay, and finally the most important thing is what, you have to provide a delay, 100 millisecond delay, and now run your program. Okay, the program is running, and if I just turn on the button, okay, the LED should get turned on. Okay, so I'll just show through the camera. Okay, we'll see now. So camera is here, USB 3. See, so you can see here. Let me call the VI. I'll minimize all the other VIs. So this is your NI Max, I think, where you can view the logics. Yeah, this one. See, when I just turn on, the LED will get turned on here. You can look, I'm controlling the on and off status of the LED. Okay, on and off status of the LED using LabVIEW program by using a data acquisition hardware. So previously we have simulated, now I'm using a real-time hardware which is connected with my system, and I can generate a digital signal which will pass through the Dac hardware. It will reach your IO terminal DIO0, and the respective LED will get turned on. Okay, so this is how, see, sorry, I have just stopped the program, turn off, and if you press stop, application will get terminated. Okay, so this is how you can generate a digital signal. You can ask, sir, you have multiple LED, how to control the on and off status of the multiple LED? Okay, simple, that is also possible. So here already I have developed a program. Okay, individually if I want to control, okay, if I want to control the on and off status, just expand. Okay, I need to select multiple IOs. Okay, I need to select what, multiple IOs. Okay, in order to select the multiple IOs, you can see there is an option to add channels. Okay, there is an option to add channel, expand. Okay, and you have to select the device that 0. Okay, line 1, hold your control button and select another line also. This is how you can select multiple line and provide OK. Okay, see, now all the lines has been added now, and directly you can just click OK. So now this DAC assistant is configured to generate 3 digital signals, because we have configured line 0, line 1 and line 2. Okay, in order to provide all these informations one by one, we need 3 different Boolean 2, or else maybe I'll put the stop button here. This is Boolean 2 and this is Boolean 3. Okay, so now to provide all these informations, okay, to connect, you can see, sir, they use the build array function, it has only one input. So just sorry, place the cursor here, expand, and connect here. Okay, 3 LEDs are now ready. Okay, and I'll minimize this, and I'll minimize this also. Okay, here you can see the 3 different LEDs here, and let me run the code. I think it's grabbing. See, 1, 2, 3. Okay, I hope you can see. I can just control all the LEDs using my digital by providing an information from my Dac hardware. Okay, so I have red, yellow, and green. Let me interchange this yellow and green. Okay, so I'm going to develop a traffic light logic. Okay, I just connected now. So I'm going to develop a small traffic light logic control where initially first red will be on for particular time duration, and then green yellow will be like start, stop, ready, go. Okay, this will be the sequence for the traffic light system, right? The same thing we can do it here. Okay, so if you want to check now, see red, I think okay, red, yellow, and this is going to be green. Okay, fine. So this, now I am just turning on, turning off through manually through the boolean button. So we will be learning how I can just create a real-time traffic light simulate signals. Mostly we'll be doing simulation. Okay, instead of doing for simulation, so I can do it through simulation also by using 3 boolean indicators in the front panel. Instead of simulating that, I have real-time hardware with me. Let me show how it is going to work, okay, in real time. Fine. So that is a logic next I'm going to develop. So if you have any queries, please let me know. Any doubts?
Sir,
Yes, sir.
sir, from sensor, how we will take data, sir? For example, if the sensor is giving light or if the sensor is giving temperature, in real time, how that data will be converted into our.
What is the sensor output, sir?
It may be a temperature or a pressure.
Okay, if it is a temperature, okay, think that you have a thermocouple, okay. So if you have a thermocouple, so the thermocouple output will be in terms of voltage, right?
Yes.
Yes. So
Yes.
that thermocouple will come under analog, okay, analog category. So then I have to choose analog input. Okay, so if you look into the data sheet, one second. This is an example. Thermocouple output will be in terms of millivolts. Okay, so I'm looking for the IOs. Yeah, if you look in the PPT, right, if you look in this PDF, right, so thermocouple comes under analog family. Thermocouple have 2 wires, okay, 2 terminal device, right? So that will be connected to AI0 plus and AI0 minus. Okay, so through this I need to connect. So once your thermocouple is connected, and then I need to develop a logic. So output will be in terms of voltage, correct? So by using MIDAC, my output will be in terms of voltage only, but we know that thermocouple output will be in terms of temperature. Then you have to go for conversion, right? So when you go for thermocouple, right, you need to go for signal conditioning, like you have to go for cold junction compensation, right? And we need to select what type of thermocouple it is, like J type, K type thermocouple. So and then you have to do some calculation so that the respective voltage will be converted into temperature, right? So that by looking into the data sheet we can do it, or else I have shown you already. We have a hardware called a compact DAC, correct? CDAC. So when I work with NI CDAC, right? So we have IO modules actually. So this is what we call as compact DAC, and this is what C series. Yeah, you can look here. This is what we call as C series modules. You can see one will be like BNC connector, another one will be like a screw terminal, jumpers, right? So we have a separate module called thermocouple module. Okay, so where thermocouples can be directly connected to these jumper wires, and inside that module itself we'll have a signal conditioning like a cold junction compensation to make it a linearization. All those things will be taken care by a signal conditioning module. Inside the module, the signal conditioning will be done and taken care by the module itself. And then when it reads a signal, when we read it in our system, the output will be directly shown in terms of temperature itself. Okay,
it is a signal conditioning circuit.
Yes, sir. Inside each and every module, we have a signal conditioning circuit available. Okay, for example, if you go for a strain module, okay, strain gauge module, right? So you
Mm.
have to go for a 2-wire or bridge configuration, right? So
Mm.
all those will be taken care inside the separate module itself. Okay, I shown right now when I open Dac Assistant, I will be selecting what type of line I'm choosing and what type of which lines I'm selecting. In the same way, if you look here, I can show here itself. For example, if I go for Dac MX, right? So if I just expand it, see if I'm going to acquire thermocouple, okay, see analog input expand, see I can measure voltage, temperature, strain. If I just expand temperature, see RTD thermocouple. When I select thermocouple, you need to select the device here. Fine. For example, this is a demo. Let me show AI0. If I select AI0, so I'll get a pop-up. But when see sir, you can select which type of thermocouple it is, J type, K type thermocouple, okay, and cold junction constant, the CJC value you can provide, and in which you want the output, like degree Celsius or degree Fahrenheit, right? All these things we need to provide, and if you provide okay, your system will automatically develop a logic behind because already it is programmed inside, fine, and your output will be converted, the voltage will be converted into temperature itself. Fine. So only MIDA can measure voltage, but if we have a lot of other C-series modules which can be interfaced with compact DAC, where you can measure pressure, flow. Even we have a module called sound and vibration module, where you can measure the vibration and acceleration and all. So we have strain module which is used to measure the strain, and if you have load cell, if you are applying a load and if you want to extract the information from load cell also, we have different modules which we should choose according to the requirement. Like this MIDAC is like a miniature hardware where it has analog inputs, analog out, DIOs, which is used for a simple data acquisition system. Okay.
Like this, shall we implement this in IoT technologies?
Yes, sir. Yeah. For example, I think you are having a temperature sensor, okay, which is going to provide output in terms of which will be providing output in temperature. Fine. So this temperature you want to push to cloud. Okay. For example, I want to monitor this value in IBM Bluemix Cloud, or if I want to monitor in Google Firebase Cloud, I need to use those set of functions. Okay, functions. I need to develop a logic here so that the data which we acquire from the sensor will be pushed to cloud itself. That is also possible.
Sir, for example, in our house or in our office, we have a temperature sensor, sir, for example.
Okay, okay.
How that temperature will be given to cloud? For example, in our house, we have this type of hardware or software, sir.
Okay, okay. Okay, I got it, sir. See, for this data acquisition hardware will be always interfaced with the system only, okay? And if you look into this hardware, it doesn't have any processor, memory, ROM, and all those things. But there is another family of hardware called Rio hardware. I already shown, right? That has a capability which can be interfaced, which has a capability to generate, and I can read and write the signal through Wi-Fi. So what we can do is, for example, if you have an internet connection in home, you can just connect your Rio hardware through internet, okay, right? So through internet, and what you have to do is you need to develop a logic to acquire the room temperature of your house, okay? For example, if you want to measure the room temperature of the house, and if the respective room temperature is high, you want to turn on and turn off the AC. It is like smart automation, okay? So what you can do is you can have a temperature sensor, connect with the Rio hardware, and whatever the data you are reading, that should be pushed to the cloud. Okay, so you have to decide which type of cloud you are going to use, whether a Google base or AWS, whatever it may be. So for that, you need to install the toolkits actually. So if I want to use a Google Firebase cloud, right, I can directly use this HTTP protocol to read and write the data. Okay, but if I want to use IBM or AWS, I need to download the separate toolkit. Then only I can access those cloud. So for example, if I use the Google Cloud, I need to give the proper URL. Okay, so that URL I need to provide, and that using that URL, you can just enter in your system and you can monitor the data. That is one more case where you can monitor all the information in your phone itself. Okay, so for that, for example, if your phone, your MyRio hardware, everything is connected to one same internet, okay, existing network, fine. What you can do is you can use some network shared variables which will be helped to transfer the data from system to system. Okay, So through your Rio hardware, you can just share the data to your mobile phone. Your mobile is another target, and your Rio is another target. So using those network shared variables and all, you can transfer the data. You can monitor. For example, if you want to think that you have a temperature sensor, you have a small fan. Okay, when the temperature is high, you want to turn on and turn off the fan through your mobile phone. That is also possible. So for that, we need to use a network shared variable.
Okay, sir. Thank you.
Okay, so like this, many things can be done by using this hardware. We need to check which hardware will be suitable for which application. So that is the important thing. Okay. Any other queries? Okay, so we'll go for the real-time hardware demonstration, which is left out. Okay, see now I'm going to explain how we are going to develop a traffic light logic. Okay, traffic light logic now. So I no need controls because we are going to write the signal depends upon the logics. Okay, so initially red, and next it's going to be yellow, and next it is going to be green. Do you know that when red is on, when a red LED is on, right, the yellow and green should be off. When yellow is on, red and green should be off. When green is on, red and yellow should be off. So we need to develop logic in such a way. We are going to exactly develop a small traffic light application with not much requirement. Simple, okay, like every 500 millisecond, one LED will be non-state. Fine. So to do that, I'm going to see same whatever the logics we have discussed from morning. With that only in a simple way, I'm going to explain. Okay, I'll be using a case structure because I have three different cases. Red. Next one is your yellow, third one is going to be your green. Okay, fine. So case 0, case 1, case 2, case 0 corresponds to red, case 1 corresponds to yellow, case 3 corresponds to green. Okay, that is nothing but ready, stop, ready, and then go. Okay, so if you look here, I'm going to use this. I can use different architecture also. I don't want to make much complex the logic. Simple logic. I'll be using this I value. I starts from 0. Okay, let me use the quotient and reminder. So I divided by 3. Okay, I divided by 3. So just look into the reminder value. Okay, so 0 divided by 3, 0, 1 divided by 3, will get a reminder, 2 divided by 3, will get a reminder here. Okay, I'll be using these reminder values that will be given to the case structure. Okay, that will be given to the case structure. It is converted into 0 and 1 here. Okay, so and then right click. This is just a simple logic. Usually we'll go for architecture to develop a complete exact traffic light logic here. Fine. And just to show a demonstration, I'm just using this simple logic here. So whenever, okay, so whenever it is 0, I want my red LED to get turned on. To get turned on this, let me give true. This is for red. Okay, and the next one is going to be false, and the third one is going to be false, and this one I'm going to connect it. Okay, so one case is done, and second, I want my yellow LED to be on. I'm going to create a false constant, change it to true, and create constant false. Okay, and the last one here, create constant false, create constant false, create constant true. Okay, simple. And I need to place a delay for each and every iteration, 500 millisecond delay. Okay, and then I'm going to run this application. So you have to look into the camera now. I need this VI, run the code. See, I can develop a small traffic. It is simple. There is no much logic here. I just want to show how we can use these type of hardware for even I can control motor. If you want to make a robotic based application also, it is possible here. My Dac hardware doesn't have any processor or memory, anything, so we cannot deploy any code here. There is another hardware called Rio, as I shown compact Rio, right? There is a same family of hardware called Rio, where it has an embedded processor and it has an FPGA inbuilt, okay, inside the hardware. where you can develop an embedded or FPGA based system using those hardware, and that can be made as a standalone system. So with that hardware, you can develop n number of applications over there. Okay, so this MyDAC hardware is meant for data acquisition, and that hardware is meant for building a standalone system. Okay, fine. So this is how you can read and write or generate and acquire the digital signal. Okay, using MyDAC hardware. Initially, we just seen how to simulate, and now we have seen how I can connect the real-time hardware and how I can develop a small application. Okay, so this is a small demo about data acquisition. Fine. So with this, the concept for acquiring an yes, sir. I'll share the LabVIEW software link. At the end, I'll share you the link. Sure, I'll post it in the chat itself, or else I'll do one thing. I'll share all the software links and then the VIs whatever I did in a folder. I'll drop it as a mail. Okay, and then after that, you can just get it from the coordinator, or if you need now, I'll put it in the chat box itself. Just give me 5 more minutes. Let me complete another concept, and then I'll put all the links here. Fine, so that you can take it from the chat directly. So next, I'm going to show how we can use analog inputs and output, and how to use the virtual instrument, because I've shown the virtual instrument, but I have not shown a demo how to work on the virtual instrument. Let me show those. Okay, how to show a demo, how to work on the virtual instrument now. Okay, fine. So I'll go for NI Max. Okay, I think I have to go with the camera. NI Max, you can see. Let me remove the connections because I need only 2 wires. So these are not required. Okay, so let me take 2 wires. Okay, I'm going to use analog input and analog output. So let me give the connection AI 0 plus. I'm going to generate a signal through function generator, and I'm going to acquire through oscilloscope. So for generation, we have to go for analog output, and for acquisition, we have to go for analog input. Okay, so one more for 0 minus. So because I have shown you the virtual instrument, but I didn't show how to work on the virtual instrument. Yeah, I just given a small connection. Simple. It's about connecting AI 0 plus to AO 0 and AI 0 minus to analog ground. That's all. Okay. So with this, I'm going to show how we can use the virtual instrument. Okay, so we have function generator. So multimeter, I don't have the probe right now. Let me open the function generator. See, here you can select the hardware. You can see here device, it is NI MyDAC, it is a real-time hardware, and I'm just generating a signal through analog output AO0. If you want to generate a sine wave, select sine wave and let the frequency be, you can enter here or let it be 35 and just select run. Okay, see, it is generating a signal with a frequency of 35.3864 hertz, and I'll come to this oscilloscope part. Okay, so where I'm going to acquire the signal, okay, through NI MyDAC 1 analog input run. Okay, see, and if you want to check also, kindly look here, whatever the frequency we are generating here, the same frequency you are getting here, 35.38. Okay, see, the same frequency, and peak to peak is 1 here, the amplitude is 1 here. Fine. If you change the amplitude, see here also it will get changed here, and if you change the frequency, see here also the frequency will get changed. Okay, time division. Okay, see, right, if you want to change the color, you can just change it, but now it is running here. Fine. So, and this is how you, and if you just change the triangle, see automatically here also we are getting triangle. If I just make it a square, we are generating a square wave, the same square wave we are acquiring through this oscilloscope. Okay, fine. So this is how you can make use of this virtual oscilloscope. See, I don't have in my cabin, we don't have such type of instruments like oscilloscope, function generator here. I have simply a small Dac hardware, and I'm using these virtual function generator and the oscilloscope. I'm generating a signal and I'm acquiring the signal, generating through function generator, and then I'm acquiring the same thing using your oscilloscope. Okay, even if you want to generate one more signal, okay, from another channel also, it is also possible. Fine. So here, if you're going to acquire any other information through channel 1, yes, you can acquire. Fine, right? So see AO, and if I select AO1, and it will automatically try to generate a signal from analog output 1 here. Fine. So even if you want to visualize that also, let me connect the wire. It's going to be 1 plus. Okay, and it's to analog AO1. Let me give the connection. And then I need one more wire, that's for grounding. So I'll go for 1 minus. Okay, and then I need to go for another ground. Okay, so for example, if I'm selecting AO1 and I'm generating a sine wave, okay, select able, okay, and see this is the second channel which is giving a noise. AO1, if I select AO1, see AO1, it is showing a triangle. Okay, so like this you can just generate I think there is a there is a loose connection here, that's why it is not showing the output properly. Let me connect it. Yes, now we'll get this. Yeah, done. So now it is AO1, AI0, sine wave. Okay, so AO1, if it is a sine wave, see it is showing a sine wave. So like this you can just acquire and generate different signals using this virtual oscilloscope and virtual function generator. Okay, so like this, if you have any analog sensors, you can just interface those kind of analog sensors uh, with your NI Dac hardware, and you can develop the logic here. Fine. So this is how you can read and write the data using data acquisition hardware. You can go for simulation based also. As I have a hardware with me, instead of showing only simulation, I've just connected the real-time hardware with the system, and I've shown like how to generate and acquire digital signal and how you can generate and acquire analog signal. And we have seen that using your virtual instrument called oscilloscope and then your function generator. Okay, so and you people are looking for software links, I'll just post it in the group itself, and or else you can just directly go to NI website and you can download. In case if you want the link, simple, see NI, you can just Google it as NI LabVIEW software. You will get this page, LabVIEW download. Okay, see, you can select this, and here you need to select the version. I'm using 2018 version. Okay, so if you want 18 version, you can go for LabVIEW 2018, or if you want LabVIEW 2020 version, you can directly click on download. It will get download and you can install. In case if you want 2018 version, see, select it, and if you want, I can directly right click, copy link address. I'll post it in the group. Okay, we can get this LabVIEW software here. So I think by today I'll share you the Multisim software link also to the coordinator. I think they can post you in your groups so that you can make use of it. Okay, fine. And even, and one more, see, I'm using LabVIEW 18, then you have to use DAC 2018 version only. You should not use 2020. All the versions should be of same type. Okay, so 2018 LabVIEW, then all the other add-on drivers, toolkits, everything should be of same version. If there is any mismatch of version, right, so we cannot download. You can download it, but you cannot develop the logics. Okay, so this is the overview of data acquisition, generation, acquisition of real-time signals. Okay, so with this from my side, my presentation is over. Please let me know if you have any queries. Now it is 4:55. We have 5 more minutes time. If you have any queries, please let me know. And even if you want my contact information, I can just put it in the last slide. And if you're looking for any support related to LabVIEW, you can just reach me through my mobile number, or you can just mail me. So this is my email ID, and that's my WhatsApp number too. Right. So if you're looking for any support related to NI technology, so you can just reach me through this. So this is my information. Sorry. So if you want, you can just take a screenshot. So if you're looking for any support related to LabVIEW, NI technology, hardware as well as software of different domains, if you're looking for any support for FDPs or for student development programs, so we support because we are the academic partners of NI. So we work on actually industry projects. At the same time, we're supporting a lot of academic institutions for conducting workshops, hardware as well as software based on different domains and technologies, and we are providing internship for students also. And if your institution wish to conduct any FTP programs related to NI technology, you can reach me through this number and through my email ID. Fine. So with this, I'll conclude my presentation. If you want, I can just post it in the Hangouts in your chat box also. If you have any queries, please let me know. So thank you once again for participating in this FTP. I'd like to congratulate Harsh Vikram sir for organizing this program. Thank you so much. Any queries?
Any queries from the participant side? Thank you.
Thank you, sir.
Was very nice to hear, and I think participants are got a very good and technical knowledge of LabVIEW software. And,
Thank you, sir. Thank you.
thank you, and we will invite you again in our next FDP or any other workshop.
Okay, sir. Sure, sure.
Thank you, Nagarjan ji, and thank you all. And this is the end of today's FDP. Tomorrow at 10 a.m. We will also learn the lab group and the and from people from the VI solution will join us for expert lecture. So we will meet at 10 a.m. and I again uh, request all of participants to kindly join the sessions